In this video, we discuss the Softmax function which can be used in machine learning. The Softmax function has worked in statistical mechanics or statistical physics, especially in the Boltzmann distribution. It turns out that it can also be used as an activation function in multi-class classification in machine learning. In previous videos, we discussed activation functions, sigmoid, and step functions. They are mainly used for binary class classification. That means we only have to deal with two classes. So this is the step function, okay, 0 or 1, and this is a sigmoid function, okay, 0 and 1, and this is the softmax function. Okay, you have 0 and then gradually rising to 1 for different inputs. Okay. Now this is the formula for the sigmoid function. We discussed this before, and this is the formula for the softmax function. The ci here is basically the same as the z here, but we have to sum over all the ci values raised to the exponent. Okay. And this ci is referred to as a logit. Okay. Now let's see what is a logit. Okay. And activation function converts logits into interpretable probabilities. In neural networks, logits are the raw unnormalized scores produced and models output layer before the activation function is applied. So in this diagram, it shows a multi-layer perceptron, MLP. So this is input layer, hidden layer, output layer. That has k outputs, okay. And this output layer will produce the predicted output that compares with the target output that give us an error. The error will be fed back to adjust the weights. Now, at the output layer, we calculate this CL, okay, using this formula, and this CL is called a logit, okay, and this is the CI here. Okay. So it is done at this this layer. Okay, so that means the sum of this value times the value at the hidden layer, okay, that fits into the output layer. Okay, it is the logit. Okay, and we feed this logit into an activation function. We obtain the final output YL. Okay, the YL here. Okay, or you can refer to this diagram. So given a set of inputs, okay, then with a set of weights, we produce the logit CL, okay. And then the activation function will calculate the probability for a given logit. Okay. That means you produce the probability of the y that equals YL given x, okay, this x pattern. Here is a simple example that shows the operation of the softmax activation function. So these are the logits, the CLs we were talking about, and we feed these values into this function. It will generate the probability shown here. Okay. And this is the piece of code that does this. Okay, so let's copy this. So we have k equals 5 values, okay, and ck, okay, these values, and then we have calculated sum, this part, okay, and we print out the sum, and then we calculate the probabilities, which is equal to exponent c to the l divided by this sum. Okay, and then we print this out. So now let's try this. So we paste this, save it, and let's compile this. Okay, so it compiles and it executes. So we get these values as shown here. Okay, so these are the lodges and these are the probabilities. Okay. Let's revisit an example that we discussed before. We use an MLP to generate the functions of a binary full adder, and in the example, the activation function is a sigmoid function. Now, in a binary full adder, we add 3 bits together, say x1, x2, x3, and we generate a carry and a sum. And this table shows the inputs and outputs. So when we add 3 bits 0 plus 0 plus 0, the sum is 0, the carry is 0. Okay. 0 plus 0 plus 1, we get 0, 1. 0 plus 1 plus 0, we get 0, 1. And 0 plus 1 plus 1, we get the sum 0 and the carry 1. Okay. And 1 plus 0 plus 0, we get 0, 1, and so on. And 1 plus 1 plus 1, we get a sum of 1 and a carry of 1. Okay. So in this case, we have 3 inputs, x1, x2, x3, and 2 outputs, carry and sum. Okay. So N1 will be 4 because we have 1 bias, and K, the number of outputs, is 2. Okay. And we use 4 hidden nodes, so the M1 is 5. Okay. You can refer to the video at this site. Now let's copy this program that we presented before. That implements the MLP of a full binary adder. So we copy this, and we call it full adder dot cpp. Paste it. So this is the program, the program. So these are the inputs. The one is x0 is for the bias. So the 0, 0, 0, 0, 0, 1, okay, and so on. And these are the label. The label is the targeted outputs to try 8 outputs, basically the same as this. Okay. And so these outputs, and these are some random ways. Okay. So from the input to hidden, okay, and this is from hidden to output. Okay. So this is the class, okay, we discussed before. This is the forward propagation, and the output is calculated using an activation function, which is the sigmoid function, okay, G, the sigmoid function, and this is the derivative of a sigmoid function. and then in the backward propagation process, we update the weights. And here at these CLs are the notches that we discussed earlier. And then we used the activation function to get the final output YL. So this is the backward propagation, and these are for testing. Okay. Now let's compile this. So we compile this G++ -O full adder. So compiles. So we get this executable. So we compiles. We execute it full adder. So these are the outputs. Okay, and when we do the test, okay, we see that we get the correct results. Okay, and these are the actual weights. Okay, the actual values. And we discussed this before. Now let's see how we can do this using the Softmax function. In our example, we have 4 different classes, 0, 1, 2, and 3. Okay, so 0 plus 0 plus 0 belongs to class 0, and 0 plus 0 plus 1 is 1, okay, to class 1, and 0 plus 1 plus 1 is 2, class 2, and so here 1 plus 1 plus 1 is 3, class 3, okay. And this class can be represented by 4 bits, 0, 1, 2, 3. So for class 0, then bit 0 is 1. Class 1, bit 1 is 1. Class 2, bit 2 is 1. Okay. And class 3, bit 3 is 1. Okay. And these are the targeted outputs. Now this is the modified implementation. So here N1 is still 4, 3 inputs and 1 bias. Okay, and M1 is 7, okay, the number of hidden nodes and bias. And K is now 4, the number of outputs, because we have 4 classes. Right? And so the inputs are still the same. So the labels, the targeted outputs, okay, will be given by the values of this table. And these are the weights as before. We extended the weights. And now, this shows the calculation of the Softmax function. As discussed before earlier, we need to calculate the sum of exponent CL, okay, the notches. Okay, we need to calculate the sum of that. And in our forward propagation, instead of using the sigmoid, we use the Softmax function, which is given by exponent CL divided by delom. Delom is the sum of the exponent CL. Okay. So this would give us the final output YL, or the probability of getting that output. Okay. And so this pin properties is pin the probabilities of the outputs or the YLs, okay, just for reference. Okay. And to predict, okay, is to use the probabilities, okay, to predict the output of this input x. And so we find from the output values, predicted output values from the forward propagation, and then we print out the probabilities for reference, and then we find out the label or the class that it belongs to. Basically, the class that it belongs to should have the maximum probability. Okay, like here, the probability of the class it belongs to should be close to 1, others should be close to 0. And so this is for testing, using some input values. Okay. So this is the output, okay, sample output. And you can see that it is correct, the output, using the testing values. So these are the probabilities, the outputs found by the MLP. Okay. And we get the maximum probability. So the maximum is here is 0.99. So it belongs to class 0. Okay, 0, 1, 2, 3. Okay, and here this 0.99 is the maximum. It belongs to class 1. Okay, and these are the inputs, of course. So the inputs, and this 0.98 the maximum, so class 2. Okay, so the inputs are 0, 1, 1. Okay, 1 plus 1 is 2, and here, okay, again, 0.98 is the maximum. So the class 3, so 1 plus 1 plus 1 is 3. Okay. So it works properly. Okay. Now, we have just copied this modified program to this directory. It is called full adder softmax.ccp. Okay, so that's the program we just discussed. Okay, there are some left over that we didn't delete. But now let's compile this. Oh, no, it should be full. So generate this executable. So you can see that these are the probabilities, okay, and these are the outputs. Okay. Oh, sorry. Yeah, okay, so this, well, I think I can modify this program. This is the old version. Make it the same as that on the website. Print. I call this print out. Change this to T. Let's compile this again. Okay, so this is in the same format as this one. This is the more up-to-date one. Okay. Yep. Lastly, let's discuss another simple example, classifying points. This is basically a simplified version of k-means clustering using MLP that we discussed in the previous video. Now let's first copy this program. Okay. So in this program, we define n1 to be 3. So that means we have two inputs, basically the xy coordinates of a point. Okay. And m1 is 7, so if we have 6 hidden nodes and 1 bias, okay. And k goes 3, that means we have 3 classes. Okay. And num samples is equal to 6. Actually, this is the number of points. Okay. K equals 3 is the number of outputs. Okay. And this is the weight. Okay. This is not used at W1. Okay, sorry. And so these are the points, xy coordinates. Okay. The sample points. We totally have just 6 points. Okay. And if the point is 0.1, 0.2, then it is class 0. You can regard it as cluster 0. Okay. And 0.8, 0.9 is class 2. And if it's 0.3, 0.6, the point is near the middle, is class 1. Okay. This point also near the middle is class 1. And 0.2, 0.3 near the upper left corner is class 0. Okay. And the other upper right corner, okay, is class 2. Okay. And so these classes are represented by the 3 bits. Okay. So class 0 is 1, 0, 0, okay, because this is position 0. 2 is 0, 0, 1, this is 0, 1, 2. Okay. And again, this is class 2. Okay. At this position, we have a 1. Okay. And these are the random ways to start with. So this is very similar to what we had before. And again, the sum expo is the denominator of the softmax function. Okay. And so here we use the softmax function to produce the probabilities. Okay, YL. Okay. Others are basically the same. Okay. And we print the probabilities, and the print rates, we don't use it here. So these are test inputs, and for the first 6, they're the same as our inputs here. Okay. Here. And then for the last 3 rows, okay, these are some testing points. Okay, so this should be class 0, class 1, class 2. Okay. So we do the test and print out the label. Okay, the classes each of this point belongs to, and this is the output. And you can see that. So it gives us the correct output, 021102. Oh, the same as this, okay. 021102. Okay, and for the rest, okay, 012 as we expected. Okay. Now let's compile this program. So we have to copy this and we call this Softmax demo.cpp. Let's save it. So this is the program that we just discussed. And now let's compile this. G++ -o Softmax demo. So it compiles. So we get this executable. Okay. So now let's execute. So we get the same results. Okay. So this concludes our discussion on the Softmax function. You're welcome to make comments below. Thank you for watching. I will see you in the next video. Okay, bye.